We have seen until now how to solve the static range queries using different approaches. And the best approach that we have seen, this one in green here, that use the sparse table and log base to n over 4 decomposition. We have to normalize the blocks, etc., which is takes single constant time for a single query and linear time for the preprocess. We can use another approach, less efficient than this last one in green here, but is very useful, especially when we deal with dynamic range queries. What's a dynamic range queries? We will go deeply in this type of queries in the next sections, but here we're going to take a quick view to understand why I will introduce this new technique here in static range queries. Because if we have a dynamic range query, which means we have updates between the queries, we're going to update the original array while we query for a range. For the naive approach, it will remain the same. There's no change here. For the dynamic programming and the static range query, we have seen that we're going to build all the answers inside a 2D array. But here, if we have a range update or a point update, which means a dynamic range query, we're going to preprocess it. The first preprocessing will be quadratic, but here to answer just a single query, we have to preprocess every time when we update the original array, which is very bad using this technique. For each time when we have an update, we have to preprocess or to pre-compute all the answers and answer the query. Same if we have the sum here, we have to rebuild the prefix sum array each time when we update the original array. So that's why the time complexity of a single query is linear here. Same with the square root decomposition. We have to rebuild all the array of blocks. But here, I think there's a technique, use what we call a lazy array, that reduce the querying of a single query to square root time complexity. For the sparse table, the same. When we update an array, we have to rebuild the sparse table. Same for the last algorithm that we have seen. Every time we update an array, we have to rebuild all the stuff, all the data structure, which is very bad if we deal with a dynamic range query. There are many techniques to solve a dynamic range query efficiently, and we can use these techniques in a static range query, because there are very efficient in both problems. The first technique that we're going to see, it's very well known technique, which is the segment tree. You can see the definition here, the segment tree. I will take the definition from this site, competitive programming algorithms, algorithm.com. A segment tree is a data structure that stores the information about array intervals as a tree. This allows answer range queries over an array efficiently, while still being flexible enough to allow quick modification to the array. Which means we're going to build a data structure, the segment tree, that allow me to answer a range query efficiently and also update the data structure, the segment tree, efficiently when we update the original array. So the advantages, it's very efficient. The code is very simple and compact and easy to implement. Disadvantages, we have to allocate more space, and there are a lot of wasted spaces as we're going to see. Let's take this example to see how to build the segment tree. If I have this original array A of size 6, containing 6 integers, first we're going to divide the original array into parts, the left side and the right side, and we keep going dividing until we reach just one element of the original array. Now this time we can build the segment tree because we have reached a leaf here. So the leaves are the elements of the original array from 0 to 0, which means that this is the range from 0 to 0, which is 0, from 1 to 1, from 2 to 2, until 5 to 5. Now we can build the intervals or the ranges. From 0 to 1, if I take the minimum here, I will put here 3, which means this is the minimum from 0 to 1. Same on the right side, from 3 to 4, which is 2, the minimum from 3 to 4. Now, on the left side, the minimum from 0 to 2, which is -1. And here, -10, which is the minimum from 3 to 5. And here, -10, which is the minimum from 0 to 5. You see here, I compute the minimum in many intervals using this data structure, which is the segment tree. The leaves of the tree are the elements of the original array. This is very important. This will help us to compute the number of nodes in the segment tree. How to compute this number of nodes? As you see, the number of nodes in the segment tree is always greater than the size of the original array. If I take, for example, this general binary tree, because the segment tree is a binary tree, the first level contains just one node, can be represented by 2 power 0, which is equal to 1. Of course, it's very obvious that the second level contains 2 nodes, 2 power 1, and the third level contains 4 nodes, etc. And to the last level contains 2 power h minus 1 nodes, where h is the height of the tree. How we can compute a number of nodes in the segment tree, we have to do the sum of all the nodes in all the levels, on each level. So 2 power 0 plus 2 power 1 plus 2 power h minus 1, which is equal, it's a very known formula, it's the formula of the sum of powers of 2, which is equal here to 2 power h minus 1. How to find that h? Now, let's back to this example and imagine that n now is a power of 2. The size of the original array is a power of 2. Let's take it here. I have, this is the original array. Let's say that contains 8 elements. So we're going to build now the segment tree. These two, they put the result here. For this two, I put the result here. For these two, I put the result here. And same here. And now, for this one, here, and the whole range is here. The last level contain the as you see, the original array, the elements of the original array. Here I have n is equal to 1, so I have 2 power h minus 1 here. I have 2 power h minus 1 nodes on the last level. So if n is a power of 2, so we have this one is equal to n. So I can say, so 2 power h minus 1 is equal to n, which is mean, I can compute h now, it's very easy. H minus 1 is equal to log base 2 of n. So h is equal log base 2 n plus 1. Okay. So, now if n is power of 2, so h is equal log base 2 of n plus 1. What if n is not a power of 2? So I will go to the next power of 2. Like in this example here, I have 6 nodes, sorry. So the next power of 2 is not of 6 is equal to 8. 2 power. How I can compute this? Same formula, but I will use the ceilings to find the next power of 2. Here I think 2 power log base 2 of 6, the ceiling is equal to 2 power, the ceiling of 2 power 5, 8 is equal to 2 power 3. But the formula here, as you see, is 2 power 3 plus 1. So plus 1 here. As we have seen, the height is equal to 2 log base 2 of n plus 1. Okay, so here, so the number of nodes is equal to 2 power 4 minus 1, which is 16 minus 1 is equal to 15. If I compute all the nodes here, I will find 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12. I have these 2 nodes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12, and 3, we have 15. So as you see, we have 15 nodes for a complete binary tree. So we have to build a complete binary tree to be able to build a segment tree. This is why we have, if n is very huge, we have a lot of wasted spaces here, as you see in this example. So the number of nodes is equal to 2, the ceiling of log base 2 of n plus 1 minus 1. Can we represent the number of nodes by another formula using just n, not 2 power n, log 2. Let's see together. We have this formula. Number of nodes is equal to 2, the ceiling of log base 2 of n plus 1 minus 1, if n is a power of 2, which means n is equal to power k, where k is a natural integer. It could be 0. What is that's natural integers. Okay. So k is equal log base 2 of n. Okay. Now, if we write n is equal to power k, we can say that 2 times n is equal to 2 times 2 power k, multiplied by 2 on each side. So, using the power properties, I can write 2 times 2 power k is equal to 2 power k plus 1. So 2 times n is equal to 2 power k plus 1. I can subtract minus 1 from both sides to get y. I subtract minus 1 here to get this one. Okay. We know that k is equal to log base 2 of n, so 2 times n minus 1 is equal to 2 log base 2 n plus 1 minus 1, which is the same formula, except the ceiling, of course, because n is a power of 2. So we can say that the number of nodes if n is a power of 2 is equal to 2 times n minus 1. What if n is not a power of 2? Same here. We adjust the ceiling. We compute the next power of 2 of n, which is m. So m is equal to 2, the ceiling of the log base 2 of n. So the number of nodes, we can say that is equal to 2 times n minus 1 if n is a power of 2, or 2 times m minus 1 otherwise, where m is the next power of 2 of n. Really easy, as you see. Let's take an example now how to build the segment tree. We're going to understand the logic behind this algorithm or this function. If I have my original array from size 6, and as we have seen, we have to build a segment tree of size 15. 2 times 2 power 3 minus 1. Okay, which is 15. I initialize the segment tree to plus infinity because we're going to use a min segment tree here, and the segment tree contains, as we have seen, 15 elements from 0 to 14, and each node represents a range. The root represents the range from 0 to 5 on the original array, and we keep dividing until reaching a leaf. As you see, we keep dividing here. Okay. These two nodes are just wasted spaces, 9 and 10, 15, 14 are wasted spaces. But we have to use it because we cannot jump an array, because as you know, the array in programming, array is a contiguous or a continuous array, continuous blocks side by side blocks. The first call will be if I call my function build from 0 to 5 and at position 0, which means here what's the minimum from 0 to 5, and we will put the minimum at the index 0 of the segment tree, not the original array. The segment tree, you put it here. I talk about this one. This one is the range. I will look for the range or the minimum from 0 to 5, and the answer will be in the index 0 in the segment tree. So we divide this range by 2. 5 plus 0 over 2, the quotient is equal to 2. So we go left. So now from 0 to 2 we take the first part, because from 0 to 5 we have the middle is at 2. We take from 0 to 2, which means here the minimum from 0 to 2 will be at the node 1. We divide 0 from 0 is the range 0 2 by 2. We have the middle is 1. So the range from 0 to 1 will be at the position 3 on the segment tree, here in the node 3. So the middle is 0 here. So we reach a leaf from 0 to 0. We will put it at index 7 on the segment tree. So we can compute this. Segment tree at position 7 is equal the element at the position 0 at the original array, which is 22. So we update the array segment tree at position 7 by 22. This is the all for the left side for this part. So we go to the right side now. So now from 0 to 1, we have from 0 to 0 done. Now from 1 to 1. From 1 to 1, which means the minimum from 1 to 1 will be at position 8 on the segment tree, which is A1, which is equal to 3. Okay. Now the left side and the right side of this node are done, so we can compute it. We can we can compute it using the minimum from between segment 7 and segment 8. Segment at seg 7 and seg 8 is equal to 3. So the minimum between 22 and 3 in this node, which is equal to 3. As you see here, I update the original array, I will add the segment tree as well the segment tree, the drawn one. This is a draw to understand what happened, and this is what will be in our code, the array in our code. So the left part is done for that node. We go to the left side is done for that node. We go to the right side. So the range from 2 to 2 will be at position 7, would be at position 4 in the segment tree. So seg 4 is equal to A2, which is -1. So we can now build or compute this node. which is the result of this node, this call. So seg of 1, this position here, seg of 1 is equal the minimum between seg of 3 and seg 4, which is -1. And we go to the right side now for the root. From 3 to 5 at position 2, we can put the middle, which is 4. We can go, so we can divide this by 2, from 3 to 4, and the left side for that one from 3 to 3, because the middle is equal to 3. We have a leaf here, so seg of 11 is equal to A3, which is equal to 5. See here. Okay. The right side for that node, from 4 to 4, seg of 12 is equal to A4 is equal to 2. Now, we can compute that node at position 5, which is the minimum from seg 11 and seg 12, which is equal to 2. Now we can compute. We go to the right, 5, 5. Range 5, 5 will be at position 6 on the segment tree, which is A5 minus 10. And we can compute that node number 2 on the segment tree, which is the minimum from node 5 and node 5 and node 6 in segment tree, which is minus 10. Now we can compute the root node plus the root node, which is the node 0. So the minimum of between node 1 and node 2, which is minus 10. Okay, as you see, so we can build a segment tree using the recursive principle to build this one. So the function to build the segment tree will use a recursive call. Keep dividing the array by 2 and assign the first half of the subtree to the left subtree, and the second the left subtree of the segment tree, and the second half goes to the right subtree until reaching a subtree of size 1 leaf. At that moment, set the current node of the segment tree by the value of that subarray and terminate the actual function call. If we write pseudo code here, our function f this function will build our segment tree. It will take the original array, the result, the segment tree that we are going to build, the start position, which means the left boundary of the array of the subarray, and here the end position, and pause the right boundary of the subarray. And here the position or the index on the subtree while we're going to update. And we have to check if we have a leaf, which means start pause is equal to end pause, we reach a leaf. We return the segment pause, which will equal to the original array at start position or the end position, because are equal. And terminate the code, which means go back to the previous code, if it exists, of course. Otherwise, keep dividing. We compute the middle, and we go to left side from the same original array and same segment tree here, but from the first part, from the start position to the middle. So we're going to put it to at 2 times pause plus 1. Once we reach the or a leaf here, we go to the right side, which is the middle plus 1 to the end position, and we put this to the right child or the right side subtree. And if we complete this call and we complete this call, we can compute now the node that the parent of these two nodes holds, which is the minimum from its two children. Here, if we have a parent position pose, so the right child is at 2 times position plus 1, position of the parent, and the right is 2 at position plus 1, plus 2, plus 2. So this is the left child, and this is the right child, and this is the parent. This is very known in binary tree. This formula is very known. Okay. So A is the original array, segment, final segment tree, start pose and pose the first index of the last index of the sub-array to split in the original array. Pose is the index of the current node cell in the segment tree. Middle is the middle of the actual sub-array. The first call will be, of course, we have to compute the segment tree for all the original array, which means from 0 to n minus 1, where n is the size of the original array, and of course we start from the root. Input here, I call it here A, call it A, which means our original array. Let's code this function. We have here all the inputs, n and the q and the original array, and here the queries, the left and the right boundaries for each query. Let's code the function. Let's call it build segment tree, or build for short. It will take the original array here, parameter here, parameters, forget original array, or the input array here, and also it will take the segment tree as a result here. This is the result, and the start position, the end position, and the position of the current node. The base case, if we have a leaf, what we're going to do here, so the segment tree at the position pose is equal to that leaf and the original array, and we come back or backtrack to the previous code. Otherwise, we compute the middle, which is equal to start position plus end position divided by 2. And of course, we call the left We want to build the left subtree from start position to the middle, the left child, and also the right child of that node. As you see, it's not very. It's easy to understand and to code and position. Of course, here you have to understand or to know as background. You have to understand how the recursion works. The seg that node that position, then the current node is equal after if we have done with the first and the second call, which is the minimum between the left child and the right child. I think it's okay. Let's call it here. First, we're going to compute the size of the segment tree, which is the ceiling of log base 2 of n 2 power, okay, 2 power, let's call it k, this one, and the size of the original array of the segment tree, sorry, is equal to 2 power, I think this is 2 power k, 2 power k, uh, 2 power k plus 1, I think. I forget the formula here, sorry, minus 1. And we have to allocate the segment tree initialize it to the query equal okay, this initialize the array to the query. I have the query here plus ability. Okay, and now we can build that segment tree from 0 to n minus 1, and the root will be at the decision. Okay, let's display the segment tree and see for this example and see how it works. Okay, let's this one now. Let's, of course, after all this we have to delete that location. I have to make sure this is the right formula. Let's come back to the presentation. I think here the formula, okay, the formula is here. M is equal to 2k, this is k, let's call it m 2 power k. M is equal to 2 power log base 2, and the sealant is k, call it k here for this, and m is equal the size of the whole 2 power. I think there is no plus 1 here. Okay. Yes. Okay. That's right. Okay, we have an error here. I think. Okay, let's the union here, because the minimum function belongs to the standard namespace. Here, okay, this one here, the famous error. 1, 2. There's a mistake here. That is a mistake. I have to be sure here. Sure about the the power of 2. I think we can write it like this. Frankly, let me forget this one. Let's use the function and see what happens. Power 2 power k. Okay. Same. Let's see the error here. Two plus 1 plus 2 . Frankly, I did not figure out what is the error here. Let's display the size and see the size of segment 3 for this input. The size is 7. No, it's not 7 the size. Must be. Okay. Sorry, guys. For this, I forget the 2 times here. I think now it's correct. Let's see it. We have this original. This one here. This original array. And we have here 2 because it's power of 2, it's very easy to build 1 here and 3 here. Now we have 2, 1, 1. So we have 1, 2, 1, 2, 4, 1, 1, and the original array 3, 2. So 1, 2, 1 to 1, 1 to 1, 2 for 1, 2 for 1, 1 to 1, 2 for 1, 3. And here the original array, the leaves. We have 3 here. Okay, sorry, we have 3 here, not 1, of course. Sorry about these mistakes. Very stupid. Okay, 1, 2, 1, 2, 4, 1, 3. That's correct. Let's see now. Let's use the right shift and the right shift for the divide by 2 and power 2 power. I think 2 times 1, 2 power k. You can write it like this. I prefer this one because it's faster to use the right and the right shift and left shift to divide by 2 or to compute the 2 power anything. This is for the 2 power k. We have a left shift and the right shift 1 to divide by 2. See it? Okay, it's the same result. Okay, this is correct. Let's make another input here. Let's take 6 and 0 for the queries because we have to focus on how to build the array original to the segment tree here. Let's take this 22, 3 minus 1, 1, 2, 3 minus 1, 5, 2 minus 10, 5, 2 minus 10, and okay, I think it's not here, minus 1, 5, 2 minus 10. Okay, I think it's okay, it's correct. Let's see it here. I have minus 10, then minus 1, minus 10, 3 minus 1, 2, 3, 3, this minus 1, minus 10, minus 1, minus 10, minus 10, minus 1, minus 10, 3 minus 1, 2, 3 minus 1, 2, minus 10, minus 10, 22, 3, and 22, 3. We have here a node, not count, and here 2 other nodes. This will be plus amenity, plus amenity, plus amenity, plus. So 22, 3. After 22, 3, we have plus amenity, plus amenity. Then 5, 2. Then plus amenity, plus amenity. Okay, the code is correct to build the segment tree using an array. Using array to build the segment tree, we have wasted spaces, as we have seen previous code. That's one. As you see, for the same example here, I have some extra nodes here. This one and this one. We can reduce the space by using pointers. We're going to build a segment tree using pointers, not an array. Here first we have to define a node, structure of a node. We use the keyword struct in C++. the node contains. If you are not familiar with this, guys, maybe I will make a whole video to understand how to build a tree using the pointers, or how to understand all these concepts. Okay, we have the value at that node, and for each node we have a left child. It's kind of linked list, and the right child, and we need two constructors. The first one, when we going to build just a node with no left child and no right child, just with the value here, and the left child is equal to the node pointer, and the right child also is equal to the null pointer. Okay, and we need another constructor if we want to build a node that we know the left that have, or the left child and the right child. So we give them the parameters here. This is for the right child now. Okay. Of course, the left child of the current node is equal to the left child given on the parameter, and the same for the right child. This is the structure of a node. Now let's build our segment tree, which will return, my segment tree will return a pointer to the root. Let's call it build. It will take, as usual, the input array, the start position, the end position of the subarray, and no need for the size here of the tree. Okay. Yeah. The base case, if we reach leaf, what will happen is we will create that leaf, that node, using this construct. Just, and we give it to the value new node here. Okay, a of the start or the end position. Same here because are equal. So for the leaf, there are no, for the leaves here, leaves, as one to do, the left is null and the right is null. So there are no left and right node, all the leaves. So that's why we are going to use this first construct. Otherwise, as usual, we compute the middle of the subarray, and we're going to build the left child or the left subtree using the recursion call for the build function using the array A, and from the start position to the middle position. This is for the left subtree or left child. Same for the right subtree. Subtree, we're going to from middle plus 1 to the end position of the sub array. Okay. If we have done with the left and the right subtree, we're going to compute the current node. We give to that current node the min between the left value and the right value of the right node, the value of the left node, the minimum between the value of the left node and the value of the right node. This is the value, and of course that current node, its left is that left child, and its right, that's the right child. I think this is all for to build the segment tree using pointers. Let's do a level order that will give me level order traversal of the tree. As you know, we can traverse the tree using different approaches: in order, pre-order, post-order, or level order. I will use the level order to give me the nodes level by level. Let's call it here first. So our node, let's call it the seg, is equal to build, function build. It will take the original array A from 0 to n-1. There is no need to compute the size here, because we want to compute only the nodes of the segment tree. There are no extra nodes here. It's not a complete. We can build a not complete binary tree. Let's call the function level order. If you don't know how it works, never mind, guys, because we will not focus on that one. Just to display the nodes in each level. It will take the array, the segment tree. I think this is okay. Let's try for this one. Okay, this is the level order. We have -10, let's see it here. Because there are no wasted spaces here, we have -10, first level. Second level, we have -1, -10 here. Third level here, we have 3, -1, 2, -10, 3, -1, 2, -10. 3, -1 are the left and the right child of this node, this one. And the 2, -10 are the left and right child of -10. Okay. And on the last level, as you see here, we have 22, 3, and 5 and 2. As you see, using pointers, I get the same segment tree as we see in the first. In this part, in this previous part. Okay, it's this one. There are no wasted spaces here. Of course, there are extra spaces, like less than if we use an array to build a segment tree. Same for this example. As you see, The level order is that this is the leaves, because here we have a power of 2, 8 nodes. We have 8 elements. Here we have power of 2. So the last level, it will contain all the elements: 3, 2, 4, 5, 1, 5, 5, 3. And the minimum from 3 to 2 is 2, 4 to 5 is 5, 1 to 1 is 1, 5 to 3 is 3. And the minimum is 2, 4, 2, and the minimum of 2 and 3, between 1 and 3 is 1. And the minimum is of 2 and 1 is 1. As you see, we have our segment tree. This is the best choice, I think, to build a binary tree or our segment tree. Instead, use an array, because if we have a huge size of elements, we're going to waste a large amount of space. Let's check the time complexity of the construction of the segment tree for both functions. The time complexity will be the same. We have two recursive calls here for this one and this one, for the same for this and this, and we have other constant operations here. So the time complexity will be, if we call it the function t of n, it will be t of n over 2 plus t of n over 2 plus c. Why over 2? Because we cut each call we divide or split the array into 2 equals parts. And c is the constant, which is the number of operations here, number of constant operations here and here. Let's call it c. And t1 on the base case is equal to 1, because here we have constant operation. We can make it an O, make O of 1. So we can write that function is equal to 2 times t over n over 2 plus c. Let's do another step. T of n of 2 is equal to 2 of t of n over 4 plus c. The same number of operations, constant operation, will be done another time on the next call. So we can develop this. We can get 4 times t of n over 4 plus 3c. Okay, let's do another step. T of n over 4 is equal to t of n 2 times t of n over 8 plus c. So the whole function will be 4 times 2 times 2 4 times 2 times t of n over 8 plus c plus 3c. We can get this function, this step. We can get this formula: 8 times t of n over 8 plus 7c. If we take a general case, we can write it: t of n is equal 2 power k. As you see here, each time we have a power of 2 here. 2, sorry for this. We have here 2, 4, 8. Each time we have 4 n over 4, 8 n over 8, 2 n over 2. Plus a constant. Here for 2 we have 1c, for 4 3c, for 7c. We can get this formula: t of n is equal to 2 power k plus t of n 2 over 2 2 power k times t of n over 2 power k plus 2 power k minus 1 times c. If we get the base case, which means this one will be equal to 1. So which means n over 2 power k is equal to 1. So k will be equal to log base 2 of n. We can replace k by its value. 2 t of n is equal to power log base 2 of n times t1 plus 2 log base 2 of n minus 1 times c. So we can get, because t1 is equal to 1, we get this formula. We know that the number of nodes in a segment tree is equal to 2 times 2 log base 2 of n minus 1. So we can compute that 2 log 2n with 2 power log base 2n is equal n plus 1 over 2. So we replace the 2 power log base 2n function, we get this formula. So we can develop this to get this formula. It's very easy to do. It's very easy in math. So we have this function c times m plus m minus c plus 1 over 2. This is the function of this both recursive functions. Now we have to look to the upper bound of this function. We have done this in the previous algorithm. The upper bound, so big O of n is equal to big O m. Here, t of n, we can say that t of n is equal to big O of n, which is the upper bound of these two functions.